Okay, so before we begin, let's just do a quick recap of what we have done last lesson. So last lesson we have learned about oxidation as well as reduction. So let's recall the definitions of these two reactions. Okay, the first definition we learned about is with regards to oxygen atom and hydrogen atom. So remember that when we talk about oxidation, we are referring to the gain of oxygen atom, and for reduction, it would be the loss of oxygen atom. For oxidation, it's the loss of hydrogen atom, and for reduction, it will be the gain of hydrogen atom. So it will be the opposite, right? So let's quickly try these three questions. Yes, could you spend some time to actually try to answer these three questions? So the question would be, could you explain whether or not SO2 has been oxidized or reduced, whether H2O has been oxidized or reduced, whether S has been oxidized or reduced. Right, so I'll try the first question together. So for the first question, it's obvious that SO2 has gained oxygen atom to become SO3. So I would say that SO2 has been oxidized into SO3 as it has, remember, we do not mention how many oxygen atom. We just say that it has gained oxygen atom to form SO3. So as long as it has gained oxygen atom, we say that it has been oxidized. Right? So SO2 has been oxidized into SO3 because it has gained oxygen atom. So we have made use of the first definition, gain oxygen atom. Again, the keyword here is atom, so make sure we talk about atom. Okay, so I give you some time to actually try question 2 and 3, right, using the similar template. Okay, give it a try. Okay, so hopefully you've given it a try. These are two very simple questions, so let's take a look at the answer. Okay, for H2O, once again, it's obvious that my H2O, it has, you can either mention that it has lost hydrogen atom, in which case it is oxidation, or you can mention that it has gained oxygen atom, in which case it is also oxidation. So H2O once again has been oxidized into O2 as it has gained, in this case I would use the gain of oxygen atom to form O2. So once again, oxidize into O2. Why? Gained oxygen atom. Again, atom, and do not mention how many atoms. That's good enough. Conversely, you can also say this, that H2O has been oxidized into oxygen as it has lost hydrogen atom to form O2. You realize that I'm using a separate definition, losing of hydrogen atom, as over here you can see H2O has lost hydrogen atom. Again, do not mention how many, just saying losing of hydrogen atom. And by definition, when you lose hydrogen atom, you're also being oxidized. Okay? So losing of hydrogen atom is also oxidation. So whichever definition you use, you would get the same conclusion, right? Okay, and for the third one, this is also very straightforward. So I would say that S has gained. Again, just say hydrogen atom, don't need to say how many. Has gained hydrogen atom to form H2S. Okay, so following the same template, you can say that S has been oxidized, has been reduced in this case. S has been reduced into H2S as it has gained hydrogen atom. So once again, for this case, is reduction. Why? Because it has gained, once again, hydrogen atom. Okay, so once again, I'm using this definition, right? So a quick recap, this definition. So once again, as a quick recap, right? When you gain or lose hydrogen or oxygen atom, it would be either one of oxidation or reduction, and this is how we actually interpret the question and how we answer it in the correct template. Okay, moving on, we have mentioned that this is not the only two definitions that we had. Recall the equation, which is, okay, I'll not erase the answer. Okay, recall this particular equation or this type of reactions, reaction number 4, where it is not possible to answer using oxygen or hydrogen atoms because there is no hydrogen atom and there is no oxygen atom for some of the reactions. Therefore, the better way to answer such questions is simply using change in oxidation state. Okay, so therefore this brings us to our third definition that we mentioned last lesson, oxidation state. So hopefully you can remember when there is an increase in oxidation state, we call that oxidation, and when there is a decrease in oxidation state, we call that reduction. So once again, going back to this question, how would you explain whether or not this is oxidation or reduction? Okay, I'll give you some time to try to deduce the oxidation number, alright, and then pause back and then check the video for the answers. Okay, so I hope you have attempted to determine the oxidation states. First of all, recall that whenever we talk about oxidation states, right, we are always referring to oxidation states of the element. Okay, so it is not correct to say that the oxidation state of copper 2 sulfate, no such thing. The oxidation state of copper 2 sulfate is incorrect. What we should be saying is the oxidation state of copper in copper 2 sulfate, because oxidation state is always of an element. Similarly, we should never say the oxidation state of SO4, no such thing. It is the oxidation state of sulfur in CuSO4, the oxidation state of O in CuSO4, the oxidation state of Zn in ZnSO4, the oxidation state of S in ZnSO4, the oxidation state of O in ZnSO4. Alright, so oxidation state is always of an element in a particular compound. Okay, so how do we determine the oxidation state? Hopefully you remember the rules. If not, you can refer back to the notes. First rule is always balance, split up ions wherever possible. Okay, so if you can't split them up, then we would always try to go for the metals first. If there are no metals, then we'll go for hydrogen. If there's no hydrogen, we then go for non-metals. And if there are no non-metals, we then lastly go for transition metals. Hopefully you recall that. If not, go and review your notes and just go through the practice to make sure that you remember how to determine oxidation states. Okay, but anyway, for this, let's try zinc. Anything on its own, remember, the oxidation state is 0. So the oxidation state of zinc in zinc is 0. It's within the element. In this case, copper SO4, the first thing we do, remember, we split wherever we can. In this case, we split. Always split them into the constituent ions. SO4 is always 2 minus, so copper will be 2 plus. And from here it's very obvious. Since it's on its own, the oxidation state of copper would be 2 plus. So for this one, again, S and O, I'll fix O first, because although both are non-metals, recall the electronegativity table, right? So O is more electronegative. We'll fix O first. O will be -2. And then S, in this case, will be +6. Because +6 minus away 2 times 4, which is -8, gives me 2 minus. Okay, so once again, if you don't remember how to do this part, refer back to your notes and the practice questions we have gone through. Okay, so with this, we know that Cu is +2, O is -2, and S is +6. Doing the same over here, we split whenever we can. So we have Zn and SO4. SO4 is always 2 minus, Zinc would be 2 plus. Fix O first, being more electronegative. S would be +6. So this would be +2. O will be -2, +6. Copper on its own, 0. Okay, so if you forget how to do this, this is very important. Once again, check back to what we have done last lesson and make sure that you recap the determining of oxidation state. Okay, so once that is done, what is next? Now we can answer the question. Okay, let's start with zinc. So what has happened to zinc? Clearly in this equation, zinc has turned into zinc sulfate. Can't be copper, right? Because it's impossible. So zinc has turned into zinc sulfate. And based on my definition, if I notice clearly, the oxidation state of zinc over here is 0. It turns into +2. And remember, by definition, when there's an increase in oxidation state, we call it oxidation. So this is an oxidation reaction. So my zinc has been oxidized into zinc sulfate because of an increase in oxidation state. On the other hand, my copper 2 sulfate has turned into copper. Oxidation state of copper here is +2, 0, reduction. Okay, so with this, I can actually answer my question. So once again, right, spend some time looking through your notes, come up with the correct template, and then attempt to solve this question and come back to check the answer. Okay, so I hope you have tried the question. So for this one, the answer would actually be as follows. Okay, so in this case, okay, zinc has been oxidized into zinc sulfate as the oxidation state of zinc. Remember, oxidation state is always of an element in a compound. So the oxidation state of zinc in zinc, right, increased from 0 to +2 in zinc sulfate. So notice that in zinc sulfate, right, so there's oxidation. On the other hand, copper sulfate has been reduced to copper as the oxidation state of copper decreased from +2 in copper 2 sulfate to 0 in copper. Alright, and since both reduction and oxidation has occurred, we call this a redox reaction. So this is the template we use when the question asks us if this is reduction or oxidation. We explain that, alright, it is oxidation, it is also reduction, so both has occurred. Therefore, this is a redox reaction. Right, so this is the template that we've talked about. Very, very important. Okay, so we have recapped how to determine the oxidation states and how to actually answer the question in the correct template. We have also briefly went through the other two definitions of oxygen and hydrogen atoms, right? So we have covered these three definitions and the template of how to answer the questions, which was what we covered last lesson. Okay, so that's very important. And of course, redox reaction is essentially a reaction where both oxidation and reduction takes place. Okay, so with this, let's quickly go through the homework on page 7 and page 8. Okay, so I think we have gone through everything up to the final fourth row. Right, so if you have not done this, please try this question before I give you the answer. Right, it's very important that you are very good at solving oxidation states very quickly and accurately. Right, so let's start with ICl7. So according to the rule, right, both are non-metals, so we'll fix the more electronegative one. Chlorine is more electronegative, so chlorine will be -1, and I have to be +7. Alright, in case you've forgotten, how do we know who is more electronegative? From the periodic table, as we move to the right, as we move upwards, they get more electronegative. That's a trend. You need to know the general trend. As they move right and up, they get more electronegative. So, excluding noble gases, who is the most electronegative element? It will be your fluorine, the most electronegative element, number 1. Remember your NOF? Oxygen will be rank 2, nitrogen will be rank number 3. So these 3 are the most electronegative elements. Other than that, know this trend. Right, up, more electronegative. Okay? So with this now, let's continue to solve the questions. Okay, moving on now, IO4. Once again, they're both non-metals, so O being more electronegative will be -2, I would be +7. Okay, once again, I'm just giving the answers, so if you have not tried the question, do try it before looking at the answer. Okay, so what do I do with this? Well, remember, first thing is I always split whenever I can. When I split them into its ions, this is what I'll get. SO4 we know is always 2 minus, and to balance the charge such that the overall becomes a minus charge, H has to be a plus. Okay, so just be very careful here. Many students will think that this minus charge here belongs to SO4 minus, but no, it's the overall charge of the HSO4. So SO4 is 2 minus, H is plus, plus, -2, you get minus. So H is +1. Again, O being more electronegative, I fix it first, and S would be +6. Okay. Similarly over here, okay, for this one, how do we do this question? Well, the only way is to again split it open. I'll get Mg and IO3. IO3 is less familiar, right? But doesn't matter because I know that Mg is always 2 plus. Metals are always fixed first. And with some induction, I can tell that since it's a 2 outside, IO3 has to be overall minus charge. So although we have not learned what is IO3, you can infer that it has to be minus charge, right? So if IO3 is minus, having 2 of it give me a 2 minus charge, which balance off this 2 plus over here. Okay, so now with this, Mg will be +2. And once again, I fix O first because O is more electronegative, O is -2, and I would have to be +5. Okay, same thing, C2O4, I can't split, both are non-metals. I'll fix O being more electronegative first, O -2, this has to be +3, 6 minus 8 minus 2. Same for this, what do? I split it open. I have Fe on one side, ClO2 on the other. So once again, who do I fix first? I can't fix Fe because Fe is a transition metal, alright? But again, with a bit of the, and I do not know what is ClO2 either. But since there's a 3 here, I can tell that this has to be a minus charge. Because if this is a minus charge, 3 of it will give me a 3 minus, and this has to be 3 plus. No other numbers would be possible for this. If I put a 2 minus, this would be a 6 plus, which is not something we have learned before. So, once again, with a bit of deduction, I can tell that it has to be minus and 3 plus. Okay, so with that, this would be a +3 charge. And once again, O being more electronegative with -2, Cl would be +3 to balance off the charge. Okay, this is a repeat question, so I'll skip this. ASO4, O is more electronegative, so O is -2, and AS would be +5. Same for this, F is more electronegative, -1, Br will be +3. Alright, since they are both non-metals, I would always fix the more electronegative element. Same over here, both non-metals, -2, +5. Same, more electronegative, O -2, +5. In this case, well, I'll fix H first. H is +1. because the rule says I fix H. Then I move on to the non-metals, O being more electronegative, minus 2. To balance, Cr would be plus 1. Okay? Okay, very, very quickly. Let's just quickly scan through this part. Okay, I've only gone through, I think, a few questions here. So let's go through this one, this one, this one, this one, and this one. Okay, so start from this one. What do I do? Alright, both are non-metals. I'll fix O first. Again, if you've not tried it, try it first before you look at the answer. Just try those that I've started. Okay, so S is more electronegative. O, to balance it, this has to be plus 3. Okay, this as well, try this. So what do? I split open. Why? Because I see something familiar, K, and therefore this is C2O4. So K is something familiar, is plus. And since there's 2 of it, I know this is going to be 2K plus, right? So this has to be 2 minus. Okay, this number here is not really important because I'm not going to use it to determine my oxidation state. Right? But I know there's 2 of it, so this will be 2 minus to balance of the charge. So K will be plus 1. O being more electronegative, minus 2. C would be plus 3. Moving on, right, just try this. O again is more electronegative, minus 2. N would be plus 5. Yeah. Okay, what about this one? Hopefully, you can recognize that we need to split this open. Why? Because it's a very familiar OH hydroxide. And we know OH is always minus. Therefore, this Cr here would now take on a charge of, overall is 2 minus, this has to be plus. Because there's 3 OH, it gives me a 3 minus charge, plus 1, overall minus 2 charge. Okay, so with this again, Cr has a plus 1 charge. I fix H first, H is plus 1, and O is minus 2. Done. Okay, moving on, OF2. Now, both are non-metals, but in this case, F is more electronegative. So F would be minus 1. I'll fix F first, and to balance the charge, O must be plus 2. So you realize that in this case, O is no longer minus 2, it's plus 2, because the rule says that we always fix the more electronegative element first. What about this? Same, the rule says we fix H first, H is plus 1, then O has to be minus 1. And for this same, we fix metals first, metals will be plus 1, H would be minus 1. So like I said earlier, the rule says that H is usually plus 1, but sometimes it will take a minus 1 charge. How do we know when would that happen? Just follow the rule, right? When we apply the rule, all these things will be taken care of. So we don't have to memorize anything, just follow the rule. Anyway, so over here, we can see that the ion present is Li plus and H. The H here is H minus, right? So what do we call H minus? You're very familiar with H plus, right? Hydrogen ions. H minus is known as hydride ions. Okay, so we call this compound lithium hydride. Right, so just know what are H minus ions called. H minus are called hydride ions. Okay, so with this, I think we have also gone through determining of oxidation states. Again, you need to be very, very good at determining oxidation states. You need to be able to determine them very quickly and very accurately, right? That's very, very important. Okay, one thing is that in school, right, most schools usually do not teach this rule that I've just gone through, right? This fix metals first, then hydrogen, then non-metals, then electronegativity, then transition metals, right? Most schools would just ask you to memorize, and they would say that oxidation state of oxygen is usually minus 2. So they will just ask you to memorize is minus 2. And then they will give you, exceptions, where under certain condition, it is not minus 2. For example, H2O2, they will tell you under this condition, the O is going to be taking the charge of minus 1 and blah, blah, blah. They will give you many, many different examples to memorize. Most schools teach it that way because they do not introduce the electronegativity concept. But we know that that's not true lah, because instead of memorizing, as you can see here, as long as we apply the rule and the electronegativity rule, we would naturally deduce that O will be minus 1. Similarly over here, as long as we apply the rule, we know that O is plus 2. So don't be confused when the school teaches, because they will teach in a totally different way. But I feel that instead of having to memorize all the different exceptions, it would be a lot easier to just understand how to deduce them. So the key thing is to actually understand this rule, which we have just mentioned in great detail, and also talk a little bit about the electronegativity concept. You don't have to know this in detail, just know the trends and who are the top 3 most electronegative elements. And with that, you can actually answer all kinds of questions, and there is no need for you to memorize all these exceptions, because the rule would take care of itself. Okay, so just take note of that. So it's very important to know the rule, even though schools usually don't teach, but I actually teach that to my students in school. Okay, so with that now, we would now move on to just quickly go through the homework on page 9 and 10. Okay, page 9 and 10. So page 9, I'll just quickly give you the answer. In each of the the question here is to determine who has been oxidized and who has been reduced. So, okay, I'll just give the answer for the first one. This will be oxidation state-wise will be 0, plus 1, minus 1, plus 1, minus 1, 0. So obviously chlorine has undergone reduction to form NaCl, while NaBr has been oxidized into Br2. Alright, so notice that I say that NaBr has been oxidized, not to NaBr. This 2, once again, is not really important. This is for mole ratio when we do the topic on mole. Right? In this case, we usually ignore them. So let me just give you the template. Again, if you have not done this, please try it and check your answer. So the question is asking which substance has been oxidized and which substance has been reduced. Right? They're not asking if this is a reduction or oxidation. They are specifically asking who has been oxidized, who has been reduced. So my answer will be that chlorine has clearly been reduced into NaCl as the, okay, I'll write short form, oxidation state of the element Cl decrease from 0 in chlorine to minus 1 in NaCl. So that's the reduction part, as the oxidation state has decreased. While NaBr, again, I left out the 2, it's not important. NaBr has been oxidized into Br2 as the oxidation state of Br increased from minus 1 in NaBr to 0 in Br2. Okay, so just check the answer. NaBr has been oxidized into Br2 as the oxidation state of Br increase from minus 1 in NaBr to 0 in bromine. While for chlorine, it has been reduced because oxidation state of Cl decreased from 0 in chlorine to minus 1 in NaBr. Okay, so in this case, we do not say that since both reduction and oxidation has taken place, this is a redox. There is no need, because the question is not asking for that. So you have to be very clear. There will be slight nuances in how the question is asked. In this case, we don't have to talk about that. And questions specifically want us to explain, although there are different definitions, right? Oxygen atom, hydrogen atom, but here we want to be explained using oxidation states. Okay, and lastly, right, one very common mistake students make is that they would say that Cl has been oxidized or Br has been oxidized. Okay, that's not true. It's not the Br that has been oxidized. It is the NaBr that has been oxidized. Okay, same. It's the NaCl that's formed. So when we say who has been oxidized, who has been reduced, it's the whole compound. The whole compound. Cl2 oxidized, NaBr reduced, the whole compound. Right? When we explain the oxidation states, then we talk about the element in a compound. Okay, and once again, some students will say, oh, 2NaBr has been oxidized. 2NaBr has been oxidized. Again, the 2 is not important. Don't put the 2, right? Okay, with this, I'll quickly go through question 2. So once again, I'll just very quickly give you the oxidation states. Right, eventually you should reach this level of speed and accuracy in determining oxidation state. When you see it, you already know it, right? So in this case, once again, let's see Na. Again, I'll omit the 2, it's just Na. It has become NaOH. So this one is clearly oxidation. H2O, omit the 2, reduction. So how do I explain? Okay, I will not write this down. I will just verbally give the answer. So check your answer. So Na has been oxidized into NaOH as the oxidation state of Na increased from 0 in Na to +1 in NaOH. H2O has been reduced into H2 as the oxidation state of H decreased from +1 in H2O to 0 in H2. That's all. Again, I do not say that reduction or oxidation has taken place. Okay. Again, I omit all these mole numbers. I don't say that 2H2O has been reduced. Right? 2H2O has been reduced is not correct. Not correct. Don't need the 2. Just H2O has been reduced. Okay. Again, I do not say this is a redox because that's not what the question is asking. For question 3, same thing. Chlorine, it's 0. Na is +1. O is -2, which is +1. Na +1. Cl minus O is -2. Cl is +1, +3. H +1, Cl -1. Okay, so for this case, same thing, Cl2. Okay, so for this case, if you try, right, you realize it's a bit different in that in the normal redox reaction we have seen so far, it's always going to be a pair, as you can see here. Na becoming oxidized to NaOH, one pair, and H2O becoming reduced to H2, another pair. It always comes in a pair. Similarly for the first one, Cl2 to NaCl is a pair. Cl2 to NaCl is a pair, or NaBr to Br2 is a pair. It's also an oxidation reduction pair, right? It's a pair. But for this case, if you figure it out correctly, you realize that, okay, there is no pair in the sense that Cl2 to NaCl, this is oxidation. On the other hand, Cl2 itself has also turned into HCl, reduction. The NaOH is not involved in this reaction. It's all just about the Cl2. It is oxidized. It is also reduced. So it is slightly different from whatever you see in these two examples, the more generic examples. Alright, so this is actually very similar to redox, but it's not redox. Okay, this is called a special reaction known as a disproportionation reaction, which you can actually turn to page 19 of your notes. At the top of page 19, you would see this redox versus disproportionation. Right? They are similar, but they're different. So what is disproportionation? Alright, disproportionation. Okay, so how would I explain this? I would say that, okay, chlorine. I'll first give you the answer. Chlorine has been oxidized into NaClO2 as the oxidation state of Cl has increased from 0 in Cl2 to plus 3 in NaClO2. That's the oxidation part. On the other hand, chlorine itself has also been reduced into HCl. As the oxidation state of chlorine has decreased from 0 in Cl2 to -1 in HCl, right? So chlorine. So in this case, you realize that chlorine has been oxidized. At the same time, it has also been reduced. Okay. So now what? So this is not a redox reaction because the same compound itself, chlorine, has been both oxidized and reduced. Alright, so like I say, if you turn to page 19, at the top of page 19, you'll see this redox versus disproportionation. Alright, disproportionation is slightly different in the sense that in disproportionation, it's where the reactant, the same reactant, is both oxidized and reduced, which is what we have seen over here. The chlorine has been both oxidized and reduced. Alright, whereas in redox, it usually comes in a pair. One oxidized, one reduced. It's always a pair. Remember? Calcium, calcium, oxidize. Magnesium, chloride, magnesium, reduce. It's always a pair. So there's a difference between redox and disproportionation. Okay? They are similar but slightly different. Right? Yeah, we'll talk more about that next lesson, so don't worry about it. But for now, I just want you to know how to answer the question, number one. And number two, I want you to be able to appreciate the difference that redox, as you can see here, it always comes in a pair, But when you see something like that, you know it's something different. This is disproportionation, right? The way you answer is pretty much similar. Okay. Okay, so with that, let's quickly go through example 11 on the next page. Okay, so once again, I'll just give you the answer. So for this, it's 2. You fix O first, -2. S is +3. This I here is -1. Many students will think it's 0. But this has a -1 over here, right? O is -2. S is +3. No, not +3. +2.5. I know it sounds a bit weird, but as long as we follow the rules, it's okay to have such weird oxidation states. It's fine, right? As long as you follow the rule, it's always going to be correct. Now trust the rule. Okay, so same thing. Now the question is asking in a slightly different way. Determine if the following reaction is an oxidation or reduction reaction. Previously, they were asking who is oxidized, who is reduced. So we just explained who oxidized, who reduced. But in this case, they're asking slightly different in the sense that they want to know, is this oxidation or is this reduction? Right? So clearly, again, I2 to I minus, this is reduction, since your oxidation number has decreased. Again, answer in oxidation states. I know you can talk about oxygen or hydrogen atom, but in this case, we want oxidation state. On the other hand, again, you see I omitted 2. S2O3 to S4O6, oxidize. Wait. Sorry, this is +2. Yeah, this is +2. Because overall is -2. Okay, so with this, I'll again verbally give the answer. Check your answer. Try it if you have not done it before checking the answer. Okay, so here's the answer. I would say that this is a redox reaction. Okay, maybe no, I'll start this way. So I2 has been oxidized to form I minus as the oxidation state of I. Okay, maybe I just write out the answer. So I would say that I2 has been oxidized into I minus. Notice I omit all the numbers in front. as the oxidation state of I has decreased from 0 in I2 to -1 in I minus. Right, on the other hand, S2O32 minus, sorry, I2 has been reduced into I minus as the oxidation state of I has decreased from 0 to -1. Yep. While S2O32 minus has been oxidized into S4O62 minus as the oxidation state of S has increased from +2 in S2O32 minus to +2.5 in S4O62 minus. Okay, let me check. So S2O32 minus has been oxidized into S4O62 minus as the oxidation state of S has increased from +2 to +2.5, or I2 has been reduced. Okay, so now since the question is asking is this oxidation or reduction, I will add on that to say that since both oxidation and reduction has occurred, this is a redox reaction. So end this part as we have mentioned last lesson, right? A bit different from how I answered the previous question, because previous question is just asking me who oxidized, who reduced. In this case, they want to know is this oxidation or reduction. Therefore, after explaining that, hey, this is reduction, this is oxidation, I then answer the question. This is actually both, so redox. Okay, redox. Okay, moving on. Part B. Okay, if you have tried part B, by the way, part C and part B are duplicate questions, so I will ignore part C. They are the same exact question. So if you have done this question, you will realize that actually no, this is neither redox nor oxidation, because there is no change in any of the oxidation states. Right? If you've done it correctly, you realize that this is not redox. No oxidation has taken place, no reduction has taken place, nothing has changed. Alright, so this is not redox. Don't be tricked. Okay, so this brings us to this question. Is all reaction going to be redox? Is all reaction going to be oxidation or reduction? Clearly, as you can see from here, the answer is no. Not all reactions are going to be redox or oxidation or reduction. Some, like this, is not. So what reaction do we call this? Okay, so I'm not sure if you know it from previous topics on salts. Okay, nitrates, all nitrates are soluble, aqueous. Sodium, all your sodium, potassium, ammonium salts, your spa salts are aqueous. Sodium again, silver chloride is insoluble solid. So if I add the state symbols, would you be able to tell me actually what reaction is this? Okay, so this is actually what we call a precipitation reaction. Remember from your salt preparation. Why precipitation? Because you produce a precipitate from two aqueous reagent. So whenever you have a solid precipitate produced from two aqueous reagent, we call this a precipitation reaction. And clearly precipitation reactions are not redox. So how do we know what reactions are redox and what is not? Okay, let's now turn to page 18. Right, let's go to page 18. Okay, and in page 18, right here, we have the list. So are all reactions redox? Answer is no. These are the reactions that are not redox. How do I remember them? Very simple. A National Day parade. Right, so A represents alkali plus ammonium salt reactions, which I hope you remember from Sec 3. Ammonium salt plus alkali gives salt, water, ammonia gas. N stands for neutralization. D stands for decomposition. And P stands for precipitation. Okay, so precipitation, we just mentioned just now, is not a redox reaction. Neutralization, acid-base. Decomposition, if you learn from your topic on metals, is basically the decomposition of metal carbonates into metal oxides and carbon dioxides. So you need to know that these 4 reactions on National Day Parade are not redox and identify them. So could you spend some time to try this question over here? Pause the video and try this question, right? Do not spend your time trying to figure out the oxidation state, but try to link them to the National Day Parade. Okay, so I hope you have tried the question. Let's quickly go through. Okay, so whenever you do such questions, we need to identify, right? A, this is a base. Metal oxides are bases, acid. So this is neutralization. Metal carbonates decompose. This is decomposition. Remember from your topic on metals. Decomposition of carbonates. Okay, for C, aqueous solid, precipitation reaction. What about for E? This is my ammonium salt. This is my alkali or my base. So this is my A in the National Day Parade. Alkali plus ammonium salt. So this is also, so this 4 represents a National Day Parade, so they are not redox. D is the only one that is not inside this National Day Parade. So D is the answer. Okay, D is redox. In fact, hopefully you can remember from your topic on metals that D is just a displacement reaction, and displacement reactions are always redox. Okay, so this is a very common kind of question, very common. They will ask you which of the following are redox or not redox. Don't go and try to figure out the oxidation state one by one. It will take you forever to do. This is the correct way. Shortcut. Identify who are not redox on National Day Parade. Solve the question. Okay. Okay. Now let's quickly now go through. Let's return back to page 13. Page 13. Yes. Let's go back to page 13 of the notes. Okay. And now I want to introduce you another concept. Alright, we have so far learned about oxidation, we have learned about reduction. Now let's go into oxidizing and reducing agent. Okay, so what is an oxidizing agent? As the name suggests, oxidizing agent is a substance that oxidizes another compound while itself gets reduced. Okay, oxidizing agent would oxidize another compound, and in the process itself gets reduced. Okay, on the other hand, a reducing agent reduces another compound, since it's a reducing agent, and in the process itself gets oxidized. So there's always 2 definitions, 2 parts to the definition of an oxidizing and reducing agent, 2 parts. Alright, but the first part is generally the more important part. Oxidizing agent oxidizes another compound. Of course, itself gets reduced. This is the second part. Same, reducing agent reduces another compound. In the process, itself gets oxidized. So there are 2 parts. We focus on the first part being the more important part. Alright. Okay, so how do we answer the question? For instance, here's an example. Copper 2 oxide has reacted with hydrogen according to this equation. So who is the reducing agent? So for this question, same thing. I'll go figure out copper is plus 2, oxygen is minus 2, 0, 0, plus 1, minus 2. So I would then deduce that, you know what, copper oxide has been reduced because there's a decrease in oxidation state, while H2 has been oxidized. Why? Because there is an increase in oxidation state. Okay, but this question is not asking who has been reduced, who has been oxidized. It's asking who is a reducing agent. So let's recall. The definition states that a reducing agent will reduce another compound. The most important definition. It reduces another compound. And in the process, it oxidizes itself. The second part of the definition. Alright, of course, remember we said the first one is more important, so we look at the first one. It reduces another compound. In this equation, we have identified that copper oxide has been reduced. So who is the one reducing it? It must be hydrogen, and therefore hydrogen is a reducing agent. Okay, so we answer the question based on the definition. Number 1, it reduced another compound, so it has reduced copper oxide into copper. Right, reduce copper oxide into copper. Why? As the oxidation state of copper decreased from +2 to 0. So the standard way of explaining. This gives me 1 mark. The more important point. Remember, this is the more important definition. If the question is 2 marks, we then bring in the second definition, which is that it oxidizes itself in the process. And then itself has been oxidized into water. Itself has been oxidized into water. And blah blah blah, the same answer. That gives me the second mark. So depending on the marks allocated in the question, we answer accordingly, 1 or 2 marks, giving always the most important definition first. Then if it's a 2-mark question, we add in the second definition. Okay, so again, this is a template for oxidizing reducing agents. Slight difference in the way we answer the question as compared to the previous type of question. Okay, so remember again, there are 2 parts to the definition for an oxidizing reducing agent. Alright, the first part is more important, and depending on the mark, we may have to explain the second one as well. So could you try this example on your own? Not only try this, 16 and 17. Try all 3 examples. So pause the video, give it a try, and then come back and check your answer. Okay, so let's go through. So this is +2, +1, +7, -2, +3, +1, -2, +2. So how do we solve this question? Very simple, same thing. Now, there are 3 different species over here. So who has been oxidized? You have to do a bit of comparison. You realize it's obvious that F2 has become F3. Again, I ignore the 5 in front. Okay, so with this, you can tell obviously that this is oxidation. Now, what about reduction? If I take a look, I would see that MnO4 minus to Mn2 plus is reduction. Okay, for the H plus, there is no difference because you start off with +1 here. Here the H is still +1. So when there are more than 2 species, you need to know how to look at it, because not all of them will be oxidized, not all of them will be reduced. It really depends. Okay. Okay, so with this now, we can solve the question. So again, who is acting as a reducing agent? Remember, reducing agent would reduce another compound. And since MnO4 minus has been reduced, okay, I can say that Fe2 plus is a reducing agent. Fe2 plus is the reducing agent. How do you explain? Well, reducing agent reduce another compound. So since it has reduced MnO4 minus into Mn2 plus as the oxidation state of Mn decrease from +7 in MnO4 minus to +2 in Mn2 plus. So it has reduced MnO4 minus, right? That's 1 mark. If it's a 2-mark question, we add this in. While itself has been oxidized into Fe3 plus as the oxidation state of Fe increased from +2 in Fe2 plus to +3 in Fe3 plus. Alright, so this is how we answer the question. Fe2 plus is a reducing agent since it has reduced MnO4 minus into Mn2 plus as the oxidation state of Mn decreased from +7 in MnO4 minus to +2 in Mn2 plus, while itself has been oxidized into Fe3 plus as the oxidation state of Fe increased from +2 in Fe2 plus to +3 in Fe3 plus. Again, remember, this would be 1 mark and the front part would be 1 mark. So depending on the mark of the question, we give the answer, right? If it's 1 mark, we can just give the more important definition, the first part. If it's 2 mark, we give both. Okay, for 16 and 17, right, you would try it and I'll give you the answer in class, okay? Okay, so once again, remember that there are 2 parts to the definition, okay? always give the more important part first. Then if it's a 2-mark question, I'll bring in the other part where it gets itself oxidized or reduced. Okay, next we move on to the next page where we talk about the common oxidizing agent. So now that we already know what an oxidizing agent does, we need to know some common oxidizing agent, right? In this table, we have quite a few oxidizing agents, but all I want you to know is these two. These two are the common oxidizing agents, right? They are new to you, KMnO4, K2Cr2O7. We call this potassium manganate 7 and potassium dichromate 6. Alright, this is very important. If you are to name the compound, you need to put in the Roman numerals. If not, you will not get the marks. I repeat, you need to put in the Roman numerals. If not, you will not get the marks, right? And if you write the formula, you need to remember the formula. Okay, so potassium manganate 7, potassium dichromate 6, they are the two most common oxidizing agent. Alright, and we acidify them. The acid is not the oxidizing agent, but the acid is needed as a catalyst. Right, and the catalyst is simply a substance. Right, it's a substance that speeds up a reaction. So the acid acts as a catalyst to speed up the reaction. Right, if not, this oxidizing agents will not work. Okay, so important, these two, acidified KMnO4, acidified potassium dichromate. So what's so special about oxidizing agents, right? So what is the significance of an oxidizing agent? Well, write this down. Essentially, an oxidizing agent tests for the presence, alright, of a reducing agent. An oxidizing agent tests for the presence of a reducing agent. Okay, so what do I mean? Give an example. Let's look at example 18. So a few drops of this acidified dichromate. So if you look at the table above, this potassium dichromate is an oxidizing agent. Alright, you add it to an unknown solution and then you see a color from orange to green. What does it mean? Since we know that oxidizing agent tests for presence of reducing agent, so when the oxidizing agent turns color, we know that a reducing agent is present. I repeat, when an oxidizing agent turns color, it indicates that the reducing agent is present. So in this case, I can conclude that X is a reducing agent. Okay, since oxidizing agent turns color, we know that reducing agent is present as it tests for presence of reducing agent. Next question student will ask, is it always going to be orange or green? No. It depends on what oxidizing agent you use. In this case, we are using potassium dichromate. And if you look at the color chart, potassium dichromate, this one, always turns from orange to green. Okay, if I were to use potassium manganate, my color will not be orange to green, it will be purple to colorless. So depending on which oxidizing agent you use, you get a different color. But whenever an oxidizing agent turns color, it always tells me that the reducing agent is present. Clear? Okay, and the colors will be orange to green, purple to colorless for these two oxidizing agents, and you need to know that. Alright, so I put star over here. You need to know the name, you need to know the formula of these two oxidizing agents, and you need to know the color change, purple to colorless, orange to green. And on top of that, you also need to know who is responsible for the purple, who is responsible for the colorless. So you need to know these ions, orange and green. You need to know the dichromate. This Cr2O7, 2- is the ion making it orange. Cr3 plus is making it green. Mn2 plus is colorless. MnO4 minus purple. Right? You need to know that as well. Right? Know the name, color change, as well as the formula of the ion responsible for the color. Okay. Of course, there are other oxidizing agents which we'll talk about it more in the next lesson. Okay. Moving on. Next page. Could you try example 19 on your own? Just very quickly try example 19. So once again, KMnO4 is an oxidizing agent. Oxidizing agent test for reducing agent. Alright, so if this oxidizing agent turns color, it tells me that X is a reducing agent. Right, same thing, X is a reducing agent. Okay, so you could fill up the blanks at the bottom here. An oxidizing agent is used to test for the presence of a reducing agent. When it turns color, it means that a reducing agent is present. Okay, and we have so far talked about two oxidizing agents. your potassium manganate 7, and your potassium dichromate 6. Know their respective color change and know the ions responsible for the color. What is the purpose of the acid in this case? Remember, the acid is to act as a catalyst to speed up the reaction. Okay, very quickly we move on to the next part, common reducing agent. Hope you'll recall, what does a reducing agent do? It reduces another compound or itself gets oxidized. So again, there are a list of reducing agents here. For now, I just need to focus on this, potassium iodide. It's a reducing agent. It tests, okay, right now, reducing agent test for the presence of an oxidizing agent, which is the opposite of an oxidizing agent. It tests for the presence of an oxidizing agent. So similarly, when a reducing agent turns color, it tells me that an oxidizing agent is present. And in the case of Ki, a very common reducing agent, which you have to know, it essentially turns from colorless to brown. Right? So colorless, I minus is the ion responsible, brown, iodine. Okay? So again, there are more reducing agents here. We'll talk about that later. For now, I just want you to know this. So a few drops of Ki. Try example 20. Okay, so I hope you have tried. Now I'll give you the answer. If not, pause the video. So a few drops of Ki, which we know is a reducing agent, right, is tested with Y. So it turns color. It tells me that Y is an oxidizing agent. Okay, Y is an oxidizing agent. So I'll keep it short. Same thing over here. A reducing agent is used to test for the presence of an oxidizing agent. When it turns color, it tells me that an oxidizing agent is present. Okay, so for today, this is what we have covered in the previous lesson: oxidizing agents, reducing agents, as well as these two color changes. All right. So if you turn to page 18, this should be what we have covered, and this should be what you should be familiar with. All right. So take some time to read through this. Okay, you need to know them very well. Okay. So for homework, what I've given the class is to actually finish up on page 19 all the MCQ walkthrough. Right. Question 1, 2, 3. 4, 5, and 6, right? Try all of them, and also finish up. Okay, so essentially finish up all the questions left in this paper, because in the notes, okay, because by now I think you should have covered the content already. So finish up all the MCQ questions here from page 22 all the way to page 27, right? Just give the questions a try, right? Finish up all the questions, and yeah, that should be all. Okay, so finish up all the questions in these notes, and I'll see you later.